So what do those tables look like? Right? They said that when we're going to want to compute probabilities, rather than going to a computer that says, oh, do some numerical integration of my density between minus infinity and t, or between u and v, I'm going to actually use tables for that. So what do those tables look like? Well, those tables actually give me the value of the CDF. So that's the area under the curve of this number. So let's say that this number is, say, u. Then we know that the area under the curve here is actually f of u, which is simply the probability that z is less than or equal to u. And here, this is for standard Gaussian, so throughout z will be a n01. Okay? Do we agree that the area under the curve here is just the probability that z is less than little u, and this is, by definition, the CDF evaluated at u, by definition of the CDF. So this table is supposed to give us these values. So this is more of a representation thing. The first thing you could have is all possible values on a particular grid, and I could give you a list, and I could say f of 1.25 is equal to blah. Okay? Now, it just so happens that we write on letter-sized papers most of the time, rather than long strip of papers where we write those lists of numbers. And so somebody was smart enough to try to fill the entire page rather than just writing a long list of values of a function. And this is actually a pretty smart idea. It says, OK, if I want to evaluate a function at a point that has 2 decimals, what I'm going to do is I'm going to look at the first decimal to the left, and I'm going to look at the second decimal on the columns here. And so, for example, if I want to compute the probability that z is less than or equal to, say, 0.76. Okay, so u is approximately equal to 0.76. How do I do this? Well, 0.76 is 0.7 plus 0.06. Okay, so I first look for my 0.7 right here. Blah, 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 blah. 0.7 is right here. And so I'm going to just look at this row. And then I look at my 0.06. This is this guy, so here's my 0.06. And then I look at the number which is on this row and that column, and that's this number. Okay? So this just tells me that the probability that z is less than or equal 0.76 is 0.7764. And that's how you read a Gaussian table. Now, this gives me just the value of being less than something, but from there, I could compute the value of being between 2 numbers, right? If I'm only interested in being at u and v, all I have to do is to subtract the value of f evaluated at the rightmost point, and I remove to it the value of f evaluated at the leftmost point. Okay, just simple rules of computing probabilities based on CDFs. Any questions about this? Okay, so here you have just a partial table. I will typically give them to you for exams. For example, they will be on the last page of the exam. For your homework, you can definitely Google Gaussian CDF calculator and just enter those things yourself. And there's a million weblets that you can use for that. So there's no point in actually using this. Should we play around with this a little bit? Yeah, we have time. OK, so let's just do a couple. So now I have a standard Gaussian. I want to compute the probability that my standard Gaussian is less than 1. So I'm going to go back to my table. 1 is 1.0 plus 0, 0. So the number I actually want to read is, can somebody tell me the answer? Probability that z is less than 1? 0.8413, that's correct. So let's write it here. Good. What is the probability that z is larger than -1? It's the same, right? And that's because this is the probability that minus z is less than or equal to 1, which is by definition, since z is symmetric, minus z I can replace by z wherever it shows up in this probability. So it's just probability of z less than or equal to 1, which we know is 0.8413. What is the probability that z is larger than 1 in absolute value? Okay, so for those things I like to draw pictures. if you're not sure, so you first draw your density like this. So this is the density of z. We know it's centered at 0. And here I'm going to put -1 and 1. And what I'm interested in is the probability that I exceed 1 in absolute value, which means that I'm interested in the area under the curve here plus the area under the curve here. Agreed? So this is what? This is just twice one of the area under the curve. And let's pick, for example, 2 times the probability that z exceeds 1. By symmetry. That's just the computation we did before. But the probability that z is greater than 1 is just 1 minus the probability that it's less than 1. So this is 2 times 1 minus 0.8413, which is equal to, I think I have this, 0.31. Okay, yeah, you don't have to go to 4 digits in general. Okay, because first of all, why don't you have to? Actually, it's a good thing to think about. Why don't you have to go to 4 digits? Like, why is the 4th digit not really relevant? Well, it's because your 4th digit is probably swallowed by this little twiddle right here. Okay, so this thing is not like a super accurate statement, so you probably don't need to provide super accurate answers. So here's something. Distribution of the final exam is 85.4. Again, this is a modeling assumption. There's no negative scores, and there's no scores above 100, but this actually still tends to model things well. So now I'm interested in the probability that a randomly selected student in this class gets higher than 90. Okay? Let's see what this is. What do I have to do here? Standardize, right? So this is the probability that x minus the mean, which is here is 85, divided by the standard deviation, which is 2, exceeds, well, 90 minus 85 divided by 2. So that's just the probability that z exceeds 2.5. Okay? And so if you go back to the table, you don't actually have anything that looks like 2.5. I just, like, it's in one of those dots, so you're going to have to trust me that the probability that you get a grade higher than 90 is actually not very high. And I'm going to write it as 0.62, but it's percent. Okay? But, you know, hopefully this was just another year. Okay, now let's look at probability that x is between 80 and 90. So here I can still do my standardization. So I'm going to go straight to writing my z in there. Okay, and that gives me 80 minus 85 divided by 2. So that gives me minus 2.5. And we've already computed the right-hand side. It's 2.5. So that's the probability that z is between minus 2.5 and 2.5. Remember, I told you that the probability that z is between minus 3 and 3 is very close to 1. So it's actually an interesting thing to see. What is the probability that z is between minus 2.5 and 2.5? And it's already really high. It's 0.98. I wrote the entire thing because I didn't want to round it at 99. Okay, and for that, I actually used the online calculator of CDF, right? I didn't bother. But you can see it's almost 99% chances that my Gaussian is between minus 2.5 and 2.5. That's really close to being completely there. Okay, so a more complicated question is, and that's one of the questions we might want to solve. Remember, we had this thing, there was this 0.0084 that showed up because I wanted the probability that Rn bar minus P larger than this number was 5%. So here, let's ask a similar question. What is x such that the probability that x is at most little x is 90%? So this you've seen before. You've all taken SATs. You know exactly what this means. This is the 90th percentile that I'm asking about. Okay? So I'm looking for the 90th percentile of this distribution. What grade should you have to be in the top 90%? Okay? So we'll see that in a second, because to actually do this, what you need to do is to read the table backwards. Okay? So you actually need to find a number. So here I didn't standardize, but if I wanted to find the probability, I wanted to find the probability the number such that the probability that z less than, say, I don't know, the probability that z less than some number is less than, is about, I don't know, 53%, then I know that this number I should be looking at. So I should look at 53%. It's right here, something that looks like 53%. And my 53rd percentile for the standard Gaussian is 0.0 plus 0.08, so 0.08. Okay? So you read it in reverse. You look for the number you're looking for in the table itself, and then you see which number gave that to me. There will be some rounding involved, right? Not all numbers you're looking for are in this table. There's many ways to round. We're going to just use a simple one. Some people take linear interpolation of different values based on how far it is. Rounding is fine. OK. So this is precisely what quantiles are supposed to do for me. So this is the definition. So percentile is just the quantile expressed as a percentage. So rather than taking a number between 0 and 100, I'm going to take a number between 0 and 1. That's just the only difference. And so the quantile of order 1 minus alpha is precisely the number that I need to plug in here so that the probability that I read is 1 minus alpha. Okay? So the 90th percentile is the one that I get when I take alpha is equal to 0.1, right? So if I take alpha is equal to 0.1, then Q alpha, or Q.1, I guess, is the 90th percentile. OK, so we can play around those things a little bit. So first question. So I said this is reading the table backwards. Reading the table for a function, right? The table was just a table that was giving you the value of the function f of something. So reading a table backward is really computing f inverse of something. So the CDF shows up in definitions. So can somebody tell me what is f of q alpha? Yes? Yeah. 1 minus alpha. Thank you. Right? So it's 1 minus alpha because f of q alpha is just this guy. So by definition, it's what it is. So now if I have a function, when I value it at q alpha, I get 1 minus alpha. So the function, I just need to invert it. So if f is invertible, q alpha is simply f inverse of 1 minus alpha. Now, let's say I want to get something. The probability that x exceeds something is alpha. What is this something? Right? What is the grade that you should get such that the probability that you exceeds that grade is only 5%? So this is q alpha again. And we're actually going to be using it this way. This is sometimes referred to as a alpha critical value. And that's typically the way we use percentiles or quantiles in statistics. So if you're used to it, it's kind of a weird thing to call q alpha something that has this probability 1 minus alpha, right? It would be more natural to write it q sub 1 minus alpha. But since we only use those guys, this is the way you need to think about them. The probability that it exceeds this thing is alpha, and that's why I call it q alpha. OK, so now if I have x, which is now z, some standard Gaussian, I'm looking for the probability that the absolute value of x exceeds something so that it gives me alpha. OK, so let's think about it for 1 second. This is exactly the question that I asked you a few slides ago when we had this 0.084 that showed up, right? The probability that some Gaussians in absolute value exceeds something, not just the Gaussian. Again, when you see a question like that, I recommend, and you don't know the answer right off the top of your head, I recommend drawing a picture. So you draw your Gaussian density. And now what I'm asking is the following. OK, so this is 0. And I'm trying to find some number, which is, say, this number here, such that the sum of those two areas is equal to alpha, right? That's the sum of those two areas is precisely the probability that absolute value of x exceeds question mark. That's the definition. Now, those two areas have exactly the same size. All right, so this is 2 times whatever area we get. And I want 2 times whatever area we get to be alpha. So what should I write here? Q alpha over 2, right? So that's Q alpha over 2. So this area should be alpha over 2, and this area should be alpha over 2, so that the probability that I'm in one of the two is just the sum of the two, which is alpha. So this is, I said this is what shows up. Really what shows up a lot is this. So as you can imagine, we're going to have to compute the quantiles of standard Gaussians quite a bit, and hopefully you will reach this sort of pathetic stage when you know them by heart like me. And this is what it looks like. 10% is 1.28. This one actually, so this is Q alpha, right? So that's when I actually give you, so if I want to compute this guy, this would give me a probability which is 20%. That's the probability of, not being sure. So 20% is like kind of a big number, and nobody really plays around with this. 5% gives you a confidence level of 10%. That's something that's more manageable, 1 in 10. And this number you see quite a bit. It's 1.645 or 1.65. OK, rounded. The one you see a lot is 2.5%, because this is precisely the one that gives you the probability that some absolute value of a standard Gaussian exceeds this number is equal to 5%. And 5% is sort of agreed upon that this is a good level of confidence, right? 5% is a tolerable level of error, or something that we want to get rid of. And so something we don't want to get. So this is precisely the number that would show up here. So what is this number? This number is 1.96. Who has taken AP Stats? All right, so if you've taken AP Stats, you ever seen, either you've seen the 1.96 or you've seen 2, plus or minus 2 standard deviations. 2 is the baby version of 1.96. So now, you could, this is going to be great, mundane conversation for your weekend parties. You know that it's not just plus minus 2, it's really 1.96. OK, and you can be super pedantic and correct people. You mean plus minus 2 standard? You mean 1.96, right? But we're going to use 1.96. All right? OK, so the quantiles are really what we're after. This is one of the things we're going to go a lot about. So this is just the inverse of the CDF. And to get them, you need to read your table backwards. But again, since you don't actually need, there's not that many values you're going to be interested in reading backwards, remembering this table is going to get you quite a bit of mileage in this class.